begin our today's seminar, and our first speaker will be Asadulina, and after Syuzanna, we'll have two short reports from our first year PhD students about their progress in their PhD project. So, Syuzanna, you're welcome. How long will it take for you to give a talk? Okay, 20 minutes plus nice. And how do you prefer to answer the questions? Just during the talk. Okay, so you can ask the questions right during the report. Okay, hello everyone. Today we're going to talk about relation effects, TNT and the surface microwaves. So in the beginning, let's talk about what is miniaturization of nerves. Okay, so we can consider the Maxwell equations with curl of electric and magnetic fields, and these equations we can decompose into 6 current equations, which can be divided into 2 groups corresponding to ITMO modes. And this polarization, I'm actually not talking about, but the dispersion is equal. And this means that the dispersion of TNT modes are equal in any direction in any frequency range. And this allows us to change the polarization of waves and this is polarization of principle based in any polarization devices. And for example, if we consider the polarizer and how it works this device in the beginning of wave propagating to vacuum medium, where the dispersion of TNT modes are equal. Next, this wave falls into an anisotropic medium, where the wire regions, the dispersion, we remove the degeneracy of polarization, and we have the phase shift between TNT and modes. And the last wave falls into vacuum medium with TNT modes degenerate, but with different polarization. And by changing the length of this anisotropic medium, we can change the polarization. For example, we can create the half-wave plate, which can transform the rotated linear polarization to another rotated linear polarization, or we can create a quarter-wave plate, which can transform the rotated linear polarization to circular polarization. So now we know what is miniaturized degeneracy and ways work and how we can work with it. And next, I want to talk about miniaturization. So, as I said, in bulk medium, the dispersion of TNT modes are degenerate in any direction and in any frequency range, and this means that they have a polarization degree of freedom. But if we minimize this medium, we will be work with localized waves, for example, surface or guided waves. And in this case, we don't have any polarization degeneracy. And my goal was to create a metasurface which can support the polarization degeneracy of TNTM surface and guided modes. And first, we consider the metasurface, which work like a Huygens metasurface, and the transmittance is almost equal 1. And this is metasurface have the overlap of electric and magnetic dipole responses. But if you look at the near fields, the dispersion of TNT modes are not degenerate, because we need to take into account the spectral dispersion between all these particles. So, next step, we know that the cylinders can support the overlap of electric and magnetic fields. And next, we wanted to investigate the dielectric metasurface, which consists of ceramic cylinders And by applying the parameters of this metasurface, for example, depth and height, we achieve the degeneracy in frequency range 7.3 to 7.6 gigahertz. And for understanding what is mean the polarization degeneracy of T and T modes, we introduce the degree of polarization degeneracy, and the first it's difference between frequency by the wave factors, and the second it's a difference between wave factors by the frequency. And the last graph shows that the difference between wave factors doesn't exceed 8 by 10 minus 3. And particular point of view, this means that to achieve the highest difference between T and T modes, our wave need to pass 50 centimeters. Okay, now you can see that we have polarization degeneracy in one direction. The next step, we wanted to investigate we want to investigate probably the degeneracy in any direction. And for this, we build the frequency contours. And here you can see that here we have the polarization degeneracy in any frequency range and in any direction. And for example, for 7.4 or 7.5, we have the degeneracy in any direction. But if you look at, oh my God, it's progress. So, but if you look in 7.6, you can see that we don't have any degeneracy, right? Because, especially in 45 degrees, because here we consider the square lattice in the surface. And when we consider that, I might draw maybe through one step. Okay. We have the equal distance, but if we look the 45 degrees, it's a square of the distance of this between these cylinders. And this is why we don't have the degeneracy in 45 degrees. So, and above the frequency, resonant frequency propagates only TMs. So, okay, we investigate the degeneracy in any direction. And next, we wanted to investigate another microwave experiment. And here you can see the distribution of electric fields. These fields was excited by electric dipole. And after that, by applying the Fourier's form, two-dimensional Fourier's form, we reconstruct the frequency contours of TM modes, and you can see that we have the good match between two ways of numerical calculation between this frequency domain and ITMO. So that's my case, but we know that we have the progressive degeneracy between T and TM modes, and after that we can propose the concept of waveguide polarization, which can work like a waveguide plate. So we know that in the tropic medium or wave propagates, and like the tropic medium, we can use the dielectric metasurface, which can support the polarization degeneracy. And here you can see that dispersions of T and TM modes, and you can see that it's almost equal. After that, we use the anisotropic medium, like changing with the surface with changing parameters, for example, diameter. And you can see that we have phase shift between T and TM modes, 0.08 P divided 8. And after that, we'll also use with the surface, which can support the polarization degeneracy between T and TM modes. So here you can see the Stokes parameters, and you can see that before anisotropic medium, we have the rotated linear polarization, and this means that Stokes parameters S2 is almost equal to 1. And after anisotropic medium, we have the circle polarization, and the Stokes parameters S3 is almost equal to 1. This means that our metasurface can work like a quadruple plate and can transform from rotated linear polarization to circle. So next, we wanted to investigate, can we achieve these results by using the meta chain and by applying the parameters of this chain, we achieve the polarization degeneracy in frequency range, like with the surface. And here you can see the difference between frequency by the wave vectors and the difference of wave vectors by the frequency. And you can see the last graph shows us that the difference between wave vectors does not exceed frequency from 7.3 to 7.45, does not exceed 8 by 10 minus 3, like the numerical calculation for metasurface. And the next step, we want to check can work this metasurface experimentally. And here you can see the experiment. Oh my God! Here you can see the experimental setup, which consists of excitation loop and scatter loop. And excitation loop excite the magnetic fields, and by scatter loop we can calculate, we can scan the normal component of magnetic fields in each point of this meta chain. And here you can see the results. The results shows us the simulation and the experiment. You can see that. Oh, so, okay, sorry. Please. So, by excitation loop, I said that we excite the magnetic fields and we got the distribution of magnetic fields, for example, for one frequency. And after that, by applying the Fourier transform, we can reconstruct the value of wave vectors at one point in one frequency. And after that, we can excite the magnetic fields in frequency range, in our frequency range, and we can reconstruct the values of wave vectors, and after that, we can reconstruct the dispersion of TM. Yes. Yeah. The same way, by the same way, we can reconstruct the TM modes, but by using the electric dipole. So here you can see the dispersion of T and TM modes, and after that you can see the difference between wave vectors of T and TM modes. Okay, it's a numerical calculation, And here it's experimental results, and you can see that they have a good match between experimental and simulation results. So we have the polarization degeneracy in frequency range, and after that, we can propose the concept of quantum plate. Here you can see the experimental setup, which consists of isotropic, anisotropic, again isotropic. And by magnetic loop, we excite the rotated linear polarization. And here you can see the excitation loop located before our chain and rotated from 45 degrees. And here you can see the scanning loop, which scan the components of magnetic fields. Here you can see the results. It's Stokes histograms, and you can see that before our isotropic medium, we have the rotated linear polarization, and this means the Stokes parameters is almost. After that, we have the circle polarization, and Stokes parameter is 3, is almost equal to 1. So here you can see the experimental setup, and you can see the experimental results. And before our photon wave chain, we have the almost rotating linear polarization, and after that you can see that we transform the polarization from rotating to linear. So here it's these results can show you maybe more information, so you see that the Stokes parameters and this line, it's mean rotated linear, and before our isotropic medium, we have rotated linear polarization. The Stokes parameters always equal to 1. And after that, we have circular. And the same in experimental, we have rotated linear and after circular. And here you can see the phase before polarizer and after polarizer for simulation and experiment. So you can see that before our polarizer, the phase is, phase like a phase delay between components of fields. And before our polarizer, the phase delay is equal 0, and after is equal P divided 2. This means that our polarization can rotate to 90 degrees, and we can rotate our polarization. And the almost same results in experiment. Before we have the phase is almost for P divided 4, and after that it's equal 3P divided 4. And you can see that, before and after, we don't have the good phase before and after for quarter wave plate. But here you can see that before and after results, we have almost 80 degrees. It's for us. Okay. My conclusions. We designed an electric metasurface which can support the polarization degeneracy between T and T modes. After that, we support the waveguide polarization. We support the one-to-wave plate, which can transform the rotated linear polarization to circular. And the last, we follow the one-to-wave plate, which consists of meta chain and also can transform from rotated linear polarization. Thank you for your attention. Thank you very much. Please, do you have any questions? Meeting is.
As far as I remember, this is like your master's results, right?
Yeah.
What did you realize during your PhD study?
Syuzanna is not a PhD student yet, actually. She's working as an engineer now. Can you repeat this?
What did you do?
Okay, so thank you so much for your question. Thank you. So, in the beginning of my work, I just researched the self-complementary metasurface and researched some leaky wave antenna. What else? So now I work with one, and we will be investigating spectral inspection. A second, I can give you the flowers and all information from the way of my head.
What this is PhD student scale. I want to things.
It's not written to answer, actually. Yeah.
No worries.
Now we prepare. I hope that we done our paper using some, and the idea was some results. Okay. Yes.
Yeah, before going to my question, I was like to add some comments. I think it was a good tradition when anyone was going to apply the new paper to give a seminar. And since now this work is almost complete and the paper is complete, so I'm decided to present the entire work for sending the paper to the journal. Yeah.
Yeah.
So I have the following question. So this is actually my short question because I don't know exactly what to say. I don't know myself. Maybe we can discuss. You show an example of a system in which TE and TMOs are degenerate and at any frequency, or this in some quite broad frequency range. But are there any other such systems? I may assume this is a particular example of metasurface, and someone may introduce or propose some other geometry metasurface, which would also have this kind of degeneration. Yeah.
Yeah.
I hope it's not unique one. Yeah. So it doesn't mean you need to take, namely, cylinders made of ceramics and so on. Maybe there's some other system can support the same kind of T and TMOs.
Yes.
Do you know in general physical requirements the system that will help to select this metasurface among others?
So I think the first ITMO also created the same metasurface, which consists of cylinders, but with how this will be oxycinco. But in this case, this metasurface can support the polarization degeneracy if we add the subplate. And the degeneracy is zero. But
what, right? If we add what? Substrate.
Yeah.
Okay.
Yes, and the second, it's a self-complementary metasurface, and this also can support the polarization degeneracy, but for 0 and 90 degrees. Here it's and here you will see the metasurface which can support the polarization degeneracy in one direction.
What's special in all these examples? What's special in all these examples that allow them to support the degenerate modes? What are the physical special response, which is can be an explanation of this effect? Why in many other metasurfaces there is no degeneration?
Okay, because here we use in our cylinders can support the overlap of electric and magnetic responses. And is it anything?
What does it mean, overlap of electric magnetic response? I mean, the response is something not quantitative. You can say this is my response. Yeah, but what is the response of metasurface?
Actually, this is sort of can support electric and magnetic. Yeah. And
isn't it something variable? That is measurable? What is the response? I mean, is there something I can measure to see that this metasurface will support the degeneration or not? Or I just need to select from these three examples: cylinders, complementary, and something else.
if we consider the cylinders, or if we consider we have the overlapping of this electric and magnetic response.
What means response? I'm just curious because there is not much formulas in paper. Therefore, I don't know what is response. Also, I think the reviewer may say what is response. What do you call response? There is something overlapping, okay, but what? Or what I can simulate or calculate or measure? To say this one should consider this one, and in this case, I will expect.
Yeah, you can simulate it, and you can see that you support the electric and magnetic fields.
Yeah, simulate what? Simulate what?
Simulate the geometry of these particles.
Okay, and what I need to compare.
And after that, you can get the electric and magnetic fields and how in this shape. And you can see that inside the cylinders we have electric and magnetic fields, which
happens in many different systems. For example, in waveguide, I also can find some places where electric and magnetic fields are orthogonal. It doesn't mean there is degeneration.
Yes, but here we have the electric and magnetic fields. But in waveguide, we need to excite the electric and the magnetic fields separate.
No, I can agree with you because every model of waveguide has necessarily electric and magnetic fields. They cannot be independently. So each mode has electric and magnetic field, and in some places they are orthogonal.
Yes, and we have TE and TM modes.
Exactly. Yeah.
Yes, and in cylinders we have TM. But in waveguides, we need to decide TE and we need to accept TM.
Here.
Here we have this. We already have.
I thought you were speaking about eigenmodes. It means there's some property that doesn't depend on excitation. It's just, the eigenmodes exist outside source. The system supports eigenmodes, but it's not a problem of excitation. So there is eigenmodes which can propagate without resources, far away from the source, to support this degeneration. So, I mean, that's what is the reason why in waveguide there is no degeneration of T and TM. They are completely different properties.
Because in waveguide we can achieve the same dispersion if we rotate our waveguide.
If the waveguide is rectangular, has square shape, or circular shape, we can rotate it and have the same dispersion, but it's the same one. If we rotate it, will remain TE mode again. It will not go. It will not turn into TM mode.
Yes.
This is a big difference.
I mean that we have the degeneracy between T and TL, TE and TE. If we rotate it,
we were speaking about the degeneration of T and TM. They're completely different things.
Yes. So
maybe it's not good to compare it with free space, because in free space there is also degeneration of the same mode but rotated in 90 degrees. While here you speak about two different kinds of field, two different orthogonal kinds of field. It's you can distinguish between T and TM only when you have some boundary condition that may be different for electric and magnetic fields. And this is exactly what happens in waveguide. On metal walls, you have different boundary conditions for E and for H. This results in this kind of different dispersion. But when you want to recover this property, you need to make somehow something similar to E vector and for H vector maybe. And you were speaking about balanced electric and magnetic polarization. Maybe this is the key to understand why this system is proper and another one not. So maybe you can think what will be the general requirement. Yes, I think that Oleg also investigated some dispersion properties of general metasurfaces in his theory. Maybe we can somehow take some conclusions from that theory and try to find explanation. Because the first question is if the same property can be achieved in some other system, or it is unique one of composite cylinders. Or maybe you can do the same thing, but with, I don't know, something else.
yes.
For example, can I create some metal system which have the same property? Or also isotropic, but degenerated response. Is it possible or not?
Yes, it's possible if we have.
Nothing self-complementary because that one is an anisotropic in plane. This one is an isotropic. Can I make a metal one?
Yes.
Also isotropic. Which kind of response? How they need to develop? No, this is a general response. So maybe the readers may be. Because one thing, if you show a particular example, or another one, if you give general recipe, this is much more interesting than
Any more questions? Okay, I have one question. I'm sorry for listening for it in advance. As you showed the experimental setup, it looks like it's quite big and the cylinders are comparable to the wavelength. We saw experiment, yes, the system is quite big and the cylinders are comparable with the wavelength. So is it still valid to call it metasurface or metachain? I think it's a philosophical question.
Okay. So what kind of say metachains, for example, metasurface?
What do you
We have.
mean by metasurface?
Oh, really? It's when we have some properties which can we can be purchased in any classical, for example, Polarization, something that we can create surface, metasurface, like you create a surface which can support it. This is why we can say that metasurface. It's something that which have the special properties.
Okay, but do we usually have one more restrictions that the elements should be much lower than the weight? So maybe I'm wrong. Maybe something have changed during
Some subway surface.
Sorry?
Surface. Yeah, and we can say that the surface should be it's some way. Always. Okay. Something like that.
Okay, so you can say that this is not subwavelength metasurface.
Okay. Thank you for your questions. I will think about it because now I think I can use
What did the detail speed?
well, meters.
Not really.
Yeah.
Everything that happens at which frequency? Some point. Well, 10 hertz is the frequency. The 5 is 6. Just something like 4.5 centimeters. This is under over 4. Right?
Yes. Yeah.
So this is a bit less. Okay. A bit less than wavelength.
Yeah. Yeah. And this is why we can say it's a sub-volume of the surface.
So I didn't see the sizes and they just.
Okay.
And you experience that we speak.
Okay. I remove this.
Sorry. Oh, so any more questions? No? So we don't have any questions in Zoom. So thank you very much. Let's